next speaker is Zim from Google, who's going to tell us a little bit about using Perfetto tracing tools. Welcome, Zim.
Thank you for the intro, Kevin. All right, so my name is Zim, and I'm here to talk to you about Perfetto recipes for Linux kernel development, but also user space. I plan to make it a bit interactive, so I have some examples I've created, some traces. Hopefully you find it interesting. What do? I work at Google as a software engineer on Android OS. I'm not part of the Perfetto team, but I work very closely with them, and I contribute a fair amount to it. Most of my job is spent helping other engineers at the company on Android debug and build tooling to understand the performance bottlenecks. Right, that's enough about me. Here's what we'll be roughly covering today. Some introduction. It was good to chat with a bunch of folks yesterday, and I saw some people are familiar with Perfetto, so hopefully the introduction is helpful anyways. This is going to be a cyclic test demo. I have to say at this point that a lot of the examples here were contributed, assisted heavily by my colleague John Stultz, who is a scheduler expert. I'm not a Linux kernel expert, but I think hopefully these examples are interesting. And then there's a instrument and user space demo, and hopefully time for questions. So yeah, let's get started. All right, so who's this talk for? Well, everyone. I really hope everyone can get something out of it. It's getting to lunchtime, so people are getting tired. But hopefully, at least you take something away, even if it's just how to set up Perfetto on your machine. If you're an expert user, hopefully some of the examples help you with your problems. And yeah, let's go on. So what is Perfetto? It's a bit of a difficult, it's an overloaded term, so hopefully this diagram helps. It's a much simplified diagram. They have a slightly more complicated one, which I would show at the end of this section. But it's all these things. It's a web UI, it's a SQL backend, it's a data format, and it's a bunch of Linux binaries. You can head over to perfetto.dev to see much more detailed and nice flashy website. And arrows are important because sort of conceptually, each of the things from right to left feed into the other. So Linux binaries provide data formats, and data formats allow the SQL backend something to query, and you visualize it with the web UI. But I will explain sort of these components very briefly from left to right. Okay, so here's a screenshot of a web UI. I will show a lot more detail about the UI and help you sort of get a grasp of how to navigate it. A lot of the navigation is WASD, so I'm sure a lot of you will be very comfortable with that. The web UI is accessible from ui.perfetto.dev, so you can capture data from any sources and just open a file on the web UI. It's important to note that the web UI doesn't have a server backend. So any data you upload is not, Google doesn't see it, no one sees it. It's completely on the client. You can turn off your internet and upload open traces with the web UI. It's a common question that we come across. And there is some Google Analytics, but besides that, just to know what pages you click, but none of your data leaves the web UI. So what does it do? It helps you, obviously, with embedded people here. So you probably have performance bottlenecks that you're debugging. Those are interested in talk right before about the Steam OS. I'm actually curious if they use Perfetto. But it helps you organize and visualize time series events. That's sort of the simplest explanation of it. Those events that could be from anywhere, depending on your field. Could be CPU, IRQ, memory, running processes, all sorts of things. So there's some opinion in how things are laid out in the UI, but there's a lot of data that you can really investigate with it. And usually, the cycles I speak to people are not very big fans of SQL. I think it's actually one of the very powerful functionalities in Perfetto. This diagram is on the website as well, and it's sort of auto-generated from the doc, so it's as true to as true as the documentation is in the code. This is a snapshot of some of the tables that exist. So, coming from our left to right, the web UI, all it does is a pretty dumb UI that just talks to a SQL database. And that SQL database, we will get to it. We'll get to how it's created, but you have a lot of tables in it. And some of these tables are opinionated based on common problems people have tried to solve, especially on Linux. And this is a snapshot of some of the tables that exist. So there's slices, which is the little rectangles, which you will see in a second. There's ftrace events, which you're all familiar with. There's sched. There's spurious sched wake-ups, which the details of these is not that important at the moment, but it's just to give you a flavor of the kinds of data that exists in the UI. And you can query all this data and join them in all sorts of interesting ways. And the arrows you see in this diagram is sort of describing some of the joins between different tables and the join columns between them. Speaking of data formats, so Perfetto supports a lot of data formats. There's the Perfetto native data format, which is if you sort of stay within the Perfetto ecosystem and use the tools on your machine, or which you can download and install on your machine to capture traces, you will be able to, obviously the Perfetto UI would be able to interpret it. But you can also capture data from multiple sources, and it supports a bunch of formats. There's the Android systrace format. There is the ftrace text output, so you can basically just dump whatever you get from your trace markers file as a file and open it in Perfetto. It opens JSON as well, and there's some interesting use cases of debugging stuff with massively nested JSON files. And I'm not going to go into that today, but if you're ever thinking of writing a JSON parser, maybe consider Perfetto. It also supports perf files. So if you capture perf record and capture a bunch of samples from CPUs or whatever trace points you have, you can open it directly in Perfetto. You don't actually have to. You can capture perf events with Perfetto, but you don't have to capture it with the Perfetto toolbox. You can take your perf files that have been generated from any machine and open them in Perfetto. It's actually not a very common, it's not a very popular feature, but you would see why. I don't think we have time to get to that anyways, but it's a really powerful tool when you get to for visualizing flame graphs. Okay, so we're getting there. The richest format is the Perfetto native data format. How do you capture data with that? What does it really do? The bottom line is, it reads data from a lot of data sources on your device. So tracefs, procfs, sysfs, and it manages, enabling data sources, and it gives you a nice configuration format to do that. And you can configure how much to read, what data sources to read, what's the buffer sizes to keep, what's the policy for the buffer sizes. It provides all this nice standardized format to access a plethora of data sources from on your Linux machine, and you can add more data sources. You can, a lot of people contribute things to it that are not even sort of Linux host machines. So there's all sorts of contributions even from VMs. So you can also trace things running in your VMs. And all of this is wrapped behind a nice, handy binary called tracebox. Behind this tracebox, there's a few tools, but this is a bit too much of implementation detail. But with the tracebox command, you can basically instantiate all of this and start a tracing session, capture data that you might be interested in. All right, so now you're an expert. Here is the website version of what is Perfetto. Obviously, I highlighted in red the things that hopefully maybe a bit familiar from what the few minutes of this talk. So on the left, you see the system tracing. You can read data from Linux ftrace, proc pullers. There's some things that are Android specific, but the Perfetto tries to be quite useful also outside of the Android and ChromeOS ecosystem. In the middle box, you see the trace processor, which is really the brains behind the data format. So on system tracing, this is everything that happens on the device. And then you get into sort of how do you've captured some standardized nice data, how do you organize it? And that's what trace processor does. So it's a C++ library, which runs in WASM in the browser, and which is behind the UI. And that's what creates all the tables and allows the data to be easily queryable, because the format they write into is optimized for writing, and SQL is a much more optimized format for reading and querying. So this is sort of the brains of the whole thing. And Perfetto UI is what most people would interact with, and you can, that's sort of the high-level overview, but you can head over to perfetto.dev/docs to see a lot more information on this. All right, getting started. I'm not going to do all of this now, but you can download the release from their GitHub page. There's official build instructions here, and there's some unofficial instructions for some additional configurations you might want, written by John Stoltz in his gist on GitHub. Some of the things there are probably on by default in most machines, but obviously you need like config ftrace, kernel config. If you need function graph tracing, you need to have those enabled. So there's a bit more, some more detail there that you might be relevant to embedded folks. All right, so hello world. Let's start with a simple config. I've said a lot, mentioned the name config a lot. What does it look like? Config is really just two, for the most part, is two pieces of information: buffers and data sources. And the buffers is what sort of the tracing daemons manage. It's what the tracing daemons manage, and you specify how much size how to size those buffers, depending on your data and depending on the size of your machine. So in this case, this is really large buffer size for what it is, but you can have as small as few kilobytes for data that's not frequent. For tracing things like SCED, you can usually overrun the buffer, and there's a few policy, in which case this is just override the ring buffer. And on the data source side, this is where you would spend most of your time configuring things, and there's lots of examples on the internet also. So you can also try some AI generation for the Perfetto configs. I've heard it's not very good, but you might get 99% there. For the most part, there's Linux ftrace data source is the data source you would care about. You specify the buffer, which is this will be in the same file. I just separated it for the slides. So you specify the buffer. By default, it picks the first buffer. So if you don't specify any target buffer, it's just going to pick the first buffer. It's 0 indexed. And then you specify the ftrace config. And this is sort of the interesting stuff. Here, I've picked a very simple config, which I think, as a start, if you just really want to get things started, SCED switch and SCED waking events are pretty interesting configs to run just to get a sense of what's happening on your system. There's a lot more you can add, but let's start with that for the hello world. And here's a simple trace output, which I will now switch over to some actual traces to guide you through this. Okay, so this is the hello world config. So the slides will be shared, and there's an appendix with all the traces here, so if you want to look at them offline, you feel free to do so. The traces were either taken on a Raspberry Pi 4 or a Intel, like a x86 NUC device. And you can see the details of which device it was taken for. So the first thing I would recommend doing when you open a trace, it opens you to this sort of timeline page, because that's considered where you spend most of the time. But one of the first things I would probably do is to head over to info and stats. I can make this a bit wider because it's a bit, okay. So one of the first things I'll do is to go to info and stats. And this shows you a bunch of detail about what was collected on the device. So it shows you the trace size, system machine, this is name, kernel version, and this is the config. So this is pretty handy because it means the traces in themselves as self-documenting of the configs that were used to capture them. And you can literally copy-paste this into a file and run it again, and you would get the same config running. There's a bunch of other things, debugging stats. I would show an example. One other thing to keep in mind, but it's not present in this trace. So if we go back to the show timeline view, note that the UI is also constantly changing. I'm currently on the auto push, which is the bleeding edge version. So you might get a slightly different UI from what I see, because there's a bunch of things like flags which you can enable, and you can change the version you are on, and plugins which you can enable. So there might be slight differences in what you see if you run this yourself. So the first thing you see is tracks for every CPU you have on your machine. I would see if I can hide this. No, I can't. Okay. The first thing you see is tracks for everything for every CPU you see on your machine. You can zoom in, so using WASD to navigate. So W zooms in, S zooms out, A, D. So. You can click on any task at any point, and this tells you, what was running on that device. On that core at the time. In this case, this is a K-worker task. You can see the priority of the task. This is a normal task. There's a bunch of more detail, but I would try to highlight the things that I typically do. This is a pretty empty, the device is not doing much. It's pretty idle, and we'll see slightly more interesting traces, but just to give you a sense. In some cases, let's see if I can find an interesting task that was woken up by something else. Let's see. There's a lot of K-worker tasks running that are not particularly interesting. Okay, all right, this is a good one. So in this case, I clicked on a task, and the nice thing about it is you get by default in this view is it shows you the wake-up latency. So you click on a task, it tells you, well, the task ran for 34 microseconds. But it was woken up at this point, and you can see the details of the wake up. So it tells you, here's the wake up time, which was on CPU 3. Here's the task, the name of the task, and here's the scheduling latency. So you can do this for any task that was woken up by CPU. For IRQ tasks, it tells you it was woken up by an IRQ, but you need IRQ information to get a bit more detail about what happened there. You can also look at the process view. So what I just showed you was the CPU specific view. You can look at the process view. In this case, I was running Emacs at the time. I guess not much happened, but you get some useful information already, right? So it tells you, over this period of time, the task was running on the CPU. And if I press M, it shows me, I get a nice bounding box of what was happening, and I can see, yes and true, this was running on CPU 1. Over here it was runnable, so it tells me, it was preempted, so it didn't get to run until it ran here, and I can click back here and see, it was preempted by this K-worker task. So you can really, dive deep into details to see. Over here it was an uninterruptible sleep. So all of this information is gotten purely from ftrace. You could, there's no, and it's sort of created a UI that is hopefully helpful for most people. But you can look at the raw ftrace events as well. So if the CPU view or the thread process view is not cutting it for you, you can go into the raw ftrace view. And it's unfortunately a little bit hard to find, but if you click on this little arrow here and click on ftrace events, then you get a sort of constantly updating view of ftrace. So if I zoom completely out, sorry, if I zoom completely in, there's no events. If I zoom out a bit, I start to get more events, and I can see the details of those events. So if I sort of wanted to figure out what are these events over here, they're not clickable, but you can see, there's just one. This was the schedule waking event. You can see detail about the trace point. And if I zoom, out a bit more, I see sort of these 3 events. So you can really navigate, and once you can either navigate that way, or if you scroll along here, you get a nice line that tells you where you are in the timeline. So a key part of Perfetto's success is in the UI is constantly giving you context about every trace event that you have and how it fits in with whatever happened on your device. So let's get back to the slide so we can get into slightly more interesting examples, but hopefully this gives you, a starting point. Oh, there's a command palette which I should also mention. So if you're familiar with VS Code, Command-Shift-B, there's tons of commands to find, and you can sort of search, and it has fuzzy search, so you can, search for a bunch of things, and there's so many events that I'm not going to go into most of them on this talk, but it's something to know that you can trigger. So just to be mindful of time, I'm going to get back into some more interesting examples in my slides. So there's an example here I captured with, from a not busy device. So I ran a toy workload. I used a tool called Dido, which was developed by a colleague at Google. I wouldn't go into the details of the config, but roughly all it does is allows you to specify as a config workloads. And I specified a bunch of CPU workloads, and so 3 different tasks running on, pinned on CPU 2, I guess, in this case. And the goal was to show the CPU frequency response to the tasks running and not running. So there's some periodic tasks running, and just to see the CPU, visualize the CPU frequency response. So if I go to the trace, this is the trace for that slide. Like I said, first thing, I head over to info and stats. So it's interesting because you can see here it does tell me that there was some data loss from ftrace, and this is something you generally want to avoid. In this case, it was fine. It doesn't really matter for my use case, but you generally want to avoid ftrace data losses. So if you do see it, you probably either have to increase the size of your buffers or reduce the number of events you're tracing. So there is some finesse into it. Here's the data source I captured. This has a bit more things. The interesting bits, buffers defined here, data sources defined here. There is scared switch and power CPU frequency. So this is what gives me the CPU frequency tracks. There's a bunch of things on process stats. This is mostly to get process tree organization, so that without these, you would just see all the threads pulled out of every process listed as a flat list. But if you provide this data source, then it scripts proc command line and figures out the process tree hierarchy and then groups threads within processes in the UI. And that's really all there is. Okay, this is a CPU frequency period to also sort of pull CPU frequency from CSFS if we don't have, if CPU frequency hadn't updated, at the start of the trace, for instance. All right, so here's a trace very similar to the one we had before, but now a lot more load. This is this task called normal prior. The tasks was running the workload. And you can see similar tracks, but now you have some additional new tracks. You have 4 new tracks for each CPU core, and you can really zoom in and see how the CPU frequency changed over time. So on this Raspberry Pi 4, I think the frequency is between 600 megahertz and 1.8. So you can see the frequency changes. You can see as soon as the task stop, the frequency ramps down back to 600 megahertz. Task start again, frequency ramps back up to 1.8 gigahertz. It took me a while to generate this trace actually, because I tried with RT tasks, and RT tasks, as soon as you run them, they ramp up to the max frequency, which was not a very interesting trace. But I was able to come up with something that showed a bit more interesting CPU frequency growth. To reproduce this, I also had to change to governor to schedule too. But anyways, the point isn't so much the workloads themselves, but I'm just providing the context on how this was generated, but that you can visualize this, right? So you probably have your own workloads that you care about, and you might want to see, investigate this. There's some additional, so I guess if I open here, this is the tasks running. As you would expect, there's not too much happening. But as I mentioned, you now get a nice this is the tree view I mentioned earlier. So for each of these top-level tasks, these are processes, and when you click on them, it shows you the different threads within them. Without the process stats scraping, you wouldn't get this hierarchical view. All right, back to the slides. Function graph tracing, this is probably one of my favorite examples. This one, John helped contribute. So I'm sure everyone here is familiar with function graph tracing in the kernel. It's a bit of a pain to reason about if you get a massive dump of function graph traces. With Perfetto, well, you can visualize all of that. So this was a simple, so I guess let's head over to the trace and see what was used. Graph. Yeah, so enable function graph. There's a bunch of ftrace events. Ftrace events keep growing. There's enable function graph, true, which is the config that enables function graph. And then you specify what's the graph root. So at what point, at what depth of your functions do you want to start capturing, function names do you want to start capturing traces for? And that's all. And you go to the trace, and boom, you have function graph traces in view with everything else. You can visualize all of this. You can, you have all your, you can highlight, you can select multiple, and this is one of actually my favorite features. Over here, you can see it's a bunch of TCP requests being received. You can pin this, for instance. Now I pin it, it takes up too much of my screen. And you can look at, a different, IRQ, no. Yeah. So you can look at a different track called IRQs, and you can reason about what was happening. So yeah, this was an IRQ that arrived. There should be a network one, soft IRQs, I guess. Yeah, so this was a network IRQ, and you can see, you can really visualize IRQs arriving on your device and the function graph in the kernel at the same time. I'm going to unpin this because it's a little bit hard to visualize. But one last thing I'm going to show in this page is, if you have multiple of these function graphs, you can condense them into one graph. So let's say over here, there's a bunch of things. It might be hard to reason about the hierarchy of all of them. You can just simply select over all of them, and you get this details panel that merges everything into one slice flame graph. So this, this is, if you're familiar with flame graphs, the x-axis is not time. This is just an aggregation, a weighted aggregation of duration spent in each depth of your functions. This is a pretty useful UI tool, in my opinion. There's a bunch of other things like pivot tables and slices, but I wouldn't go into it now. And let's move on a bit more to even more interesting demos, hopefully. So this is a demo on a cyclic test. It's the RT cyclic test in the kernel. This John really helped me a lot with, so I have to thank him again for it. He also has a handy script that helps run this test. So I guess what the test is basically, I guess, a test used in the kernel to measure wake-up latency of tasks. So you run it, and you get some statistics on wake-up latencies of tasks. Like it runs a bunch of RT0, highest priority RT tasks. You can see some statistics from it. Here's an example run. So in this case, this is just running the cyclic test. Like his script is also linked in the slide, so you can take a look offline. It just runs a cyclic test, and it shows you the average, the max wake-up latencies across the different cores. This is on his Nook device, I believe. And things are fine. Like, there's no egregious wake-up latencies. But you add some load, so he runs this, now this is the script that he runs, which does a bunch of iperf work to simulate, to create network requests, and a bunch of DD for block load, for IO load. And you can see there's a wake-up latency of 1.1 milliseconds on CPU 4, and that's not great for an RT high prior task. And where did this go? I guess this is the challenge, right? So he ran this and then captured a trace, and this is what the trace I'm going to show you here. So this is what a trace looks like. Well, where is the scheduling the wake-up latency? Now this is the goal of this demo is to really show how much SQL can shine in cases like this, and I am going to hopefully show incrementally this demo if I think I have enough time. If I can type fast. So select start from sched. So this is the sched table, and it tells you if you do this, I'm just going to say limit 100. So this tells you every sched event that happened in the trace. Now, not very useful to find things. There's a ton of them. If I said, count from sched, select count from SCAD. So that's there's 1.6 million SCAD events in this trace. Now, SCAD just tells you everything that was running on the CPU. So what you generally want, if you want to understand things like scheduling latency, is a very similar table called thread state. And thread state has even more because it tells you all the thread state, all the transitions of your process state. So D, R, all of the usual stuff you're familiar in the kernel. I'm going to pick up the speed for time. And I'm just going to jump straight in to give you the query, which is helpful. So you can look at thread states, but this doesn't really help you find the long task you're looking for. So what do we know? We know the name of the task. The thread was called cyclic test, so we can do that. We can see that this is the task running. There's a lot of SCAD happening, but good luck finding the needle in the haystack. So now we can join with a table called thread using a unique TID column in these tables. And what this gives us, if I just show an example of this, so it tells me a bunch of timestamps, duration, CPUs, the thread name, thread IDs, more information than I need. I probably want to then filter down to where name of the thread equals cyclic test. And I'm trimming down, but there's still a lot of things. Maybe I can say count just to see progressively where things are going. So only from the cyclic test in thread states there is 169,000. So we're getting there. Okay. So and duration of task and state is in R. So in this case, I want to see thread states where I'm waiting for CPU, and now I'm down to 56,000. But I also want to then see the ones where the duration is greater than 1 millisecond. And now I'm down to 28, so we're almost there. But the final bit, and I'm kind of cheating here because I know, is the main thread, the cyclic test has a worker thread that does a bunch of setup, and that thread is not an RT thread. So I want to exclude that thread from these because there's 28. Wake-up latency is greater than 1 millisecond seems a bit strange. And if I can easily do that by saying, well, and it's not a main thread equals 0. I know I get just one task now. So, well, where's the task? At this point, sorry, I go back here. I can then see all the details of this task. So now I can see the task. I can see, well, it was woken up by an RQ. I believe this is the RT timer. There's a bunch of detail here, but this is not super useful yet. So I can go back to the timeline, and this is one useful feature which, if you were sleeping all for the rest of the talk, this is the one feature to wake up for. And it's called show debug track. So you have a list of things with timestamp, duration, that's sort of the key columns in Perfetto in most tables. You can just simply say show debug track. And what it does is it takes this information, this timeline, this event, and places it in a new track in a trace. So now you've created a track yourself. And you can then easily find where that track is. And you can see here that it says cyclic test, and you can click on this, and boom, this is our 1 millisecond task, wake-up latency. So if we zoom into this, yes, this is, we click on running, you can see it's a priority 0, so RT 0 task, running on CPU 5, but had a 1.6 millisecond latency. Why? We can pin this and quickly head over to CPUs, because we collected RQs. So we can see, well, first of all, what was running on CPU 5. Let's also pin that. So there was an iPerf task running on CPU 5. Unsurprisingly, we were using that to create load. And we can see that it was handling a network receive request. So this was an RQ it was receiving, and was running the bottom half of the RQ, which runs as highest priority, and we'd even preempt an RT0 task, even though the actual task that was running was a SCAD normal task that shouldn't preempt an RT task. This really is the key point of the demo, that you can use sort of SQL in addition with the UI to really navigate traces. I'm almost out of time, but I'm going to ask Kevin how much to rush. I have 5 minutes. Okay. So I'll quickly go through. This is what we covered. And lastly, Instrumenting user space. So this is a very contrived example, just to show more navigation in the Perfetto UI. Simple workload, simple C program. All it does runs an a contrived benchmark to measure the effectiveness of read ahead, IO read ahead. So in one case, here is the sort of core of the benchmark. So there's a run read test that takes a Boolean use read ahead or not. If it's using read ahead, if it's not using read ahead, it advises the file to open to fadvice random so that the kernel doesn't use read ahead for it. Otherwise, it just does it. This is the read, so custom read block, just does a linear read, so the kernel will read ahead. If you run the benchmark, before running the benchmark, it's helpful sometimes to see user space workloads alongside the kernel events, and you can inject user space events into the trace marker directly. You can write the trace marker, and because Perfetto understands Android systrace, Android systrace has a convention of some trace marker. So this cryptic BE basically means begin and end, and there's a format for it where B, the TID of the task, and if you read about A trace on Android, this format will be clear, but this is not the point of it anyways. The point is that you can inject details into the trace marker. There's a better way to do it with the Perfetto SDK, but it's a bit more involved, and as an embedded developer, you're probably too busy to do that anyways. So you can inject things in the trace. All I'm doing is just I want to understand where am I reading with read ahead and not read ahead, so I can see this information in the trace when I open it. Here's a simple benchmark. You can see I'm basically alternating. So once I write with read ahead, drop caches, write without read ahead, drop caches, and you can see the throughput is alternating between 37 megabytes per second and 16 megabytes per second roughly. You can see an average, which is, if all you looked at was the average, it would be a pretty misleading value because you have a bimodal distribution here. And well, let's look at the trace in the last minutes we have. So this is the trace. This is the trace markers we added. So you can see with read ahead, takes about 104 milliseconds to read. Without read ahead, more than doubles the time. And it goes, and I ran, I think, 10 of this. And what can you do from this? So one of the interesting things you can do is you can click on what these rectangles are called slices. It's a pretty hidden feature as well, which is a bit annoying. But you can say click slices, show slices with the same name, and it basically searches the entire trace and shows you slices that have the same name as this. And you can quickly see, this is the duration column. You can sort by, highest to lowest. And you can do the same thing for without read ahead. And you can also sort highest first. And you can see sort of very clearly the difference in the tasks. You can reason about what's happening in the without read ahead. So you can see lots of IO stalls, lots more IO stalls. You can zoom into the CPU to see what's happening. You can zoom into the IRQs to see what's happening over that period. That's pretty much it. I can go back to present mode and breeze through the rest of the slides. So yeah, that's actually it. Okay, thank you.
Can you run the web UI locally, fully locally? So I wouldn't have to use any sort of internet connection?
Yes, so the question is whether you can run the web UI fully locally, and the answer is yes. You can build it locally. It's a TypeScript project, so there's very straightforward commands, literally UI/build.
Thank you.
I didn't see an example of this. Can you grab data from a target? Is the SQL database on the same machine as the target, or can you do like a host target type of setup for grabbing trace data?
Sorry, could you please rephrase?
Well, can you have, is there any way to gather data from a machine where Perfetto's not running, or?
Yeah, good question. So, yeah, can you grab a trace from a machine where Perfetto is not running? Yes, you can, but you typically cannot capture in the Perfetto native data format. So If you have some data, for instance, if you have perf on that machine, you can capture perf events. You can also capture from the trace marker directly, so you get the raw ftrace output, and you can open that directly in Perfetto. So you don't need to have Perfetto in your machine. You lose out on some, you have to do the configurations yourself on the trace FS, but you can, and if you, whatever ftrace output, you can open it in Perfetto.
Okay, thanks.
But Tracebox binary is available for lots of, you can run Tracebox, if you have Tracebox on your target, you can run that locally, right? And then move the trace over to the machine with the web browser.
Yes, that is correct. That is correct. So once you run, if you do run trace on a machine, you can the trace is self-contained, and you can open it anywhere and share it with people. There's actually a nifty share option in the trace.
How do you discover what ftrace events are helpful? And like, it looks clever from ftrace events, but from the get-go, I don't know which one I should enable.
Yeah, it's a good question. So how do you discover ftrace events? It's a lot of trial and error. I think I mostly copy-paste configs. If you work in a particular subsystem, it's a bit obvious. Maybe it's usually useful to start with capture everything, see where there's data loss, and then see the list of everything and trim it down. So there's no good answer to that, unfortunately, but there's lots of snippets online. There's a lot of documentation. So in Perfetto dev/docs, there's a lot of information on that.
Thank you. For those of us who don't want Google Analytics, can we self-host a web UI and run that in Firefox?
Yes. So that was literally the same question. You can self-host the web UI and run it yourself. You also don't need to use the web UI, actually. So the way this is structured is there is the web UI, which talks to a SQL database, which is populated by a C++ library called trace processor. And you can run trace processor as a binary on your machine. You don't even need a web UI. And then you can issue your SQL commands to it directly. So I actually do that quite a bit. If I don't, on a terminal, I don't want to open a UI.
Okay, thanks. And a separate small question, do you have plans to package the binaries and the libraries in Debian at some point?
In Debian?
Yeah.
I don't work on the Perfetto team, so I cannot answer for them. But there are release binaries on the GitHub page. So you don't have to build from source if you don't want to, and you can just download. And there is available release binaries for most architectures, except RISC-V, as far as I know. But ARM64, there's definitely, on my Raspberry Pi, I was able to just pick a release binary.
Okay.
Do you have a slide for GPU capturing? Because I've used that, and it's the coolest thing of Perfetto, actually.
Yeah, GPUs, I think, famously tricky to. Yeah. I don't have a good answer for GPU tracing. I heard yesterday from someone that there is some files that you can get information from about GPUs, but
Yeah, it actually works really well. And yeah, that's probably one of the coolest.
Yeah. So also, if there's a file on your machine, Perfetto is not just about ftrace events. It polls files regularly. So there's a bunch of information that we poll regularly from files. For instance, UMA_just is a pretty important information in Android, and we poll that, and you can configure that polling interval.
Got a question from an online viewer. He's asking, can you easily look at two different times in the same trace and compare them?
Yes, you can. So two different times in the same trace.
Yep, that was the question.
Well, look at is a bit, I would need some definition of that, but you can technically open two different tabs, but what I thought the question was about is, can you look at two different traces with the same timeline? And that you can, but.
That's probably what he meant, I assume.
Are there plans to add support for the common trace format?
Sorry, I didn't get the last word.
The CTF, common trace format, that like Babel trace and LTTNG, those.
BTF.
I thought it was CTF.
Did you say BTF?
CTF, common.
CTF. Sorry,
Yeah.
I'm not familiar with that.
Okay.
Yeah. But for what it's worth, a lot of people have contributed a lot of formats. So I'm not familiar with it, doesn't mean it doesn't exist in Perfetto. I'm just saying I don't know. Yeah.
Thanks. Thanks for this presentation. I have a little question, okay? Perfetto is for CPU usage, okay? Do you plan to extend Perfetto to memory usage?
There's a lot of information today about memory in Perfetto. Unfortunately, I didn't have the time to show them, but you can add VM stat information, you can get this RSS stat information, there is a ton of memory you can get.
Okay, thanks.
Thanks for showing how polished it is. Do you find yourself reaching to Kernel Shark? Because Kernel Shark also does some stuff like that? Or do you think Perfetto is a superset from of what?
Yeah, I was anticipating a question about Kernel Shark, and I didn't do my homework. I have never used Kernel Shark. I know of it, but I guess I don't know. If you have used Kernel Shark, try Perfetto and see what works for you. But I'm not going to also shit on any tool, so.
Okay, so it's a Qt application which has some of the UI elements that you have. Okay. There is also func graph with redval. Do you already visualize that in Perfetto? It allows you to show the return values, which is very useful.
So there's a fun graph with what?
Func graph with redval. It allows you to show the return values of kernel functions.
You can see that already in, so you can enable this kprobe support at least. Is this return values based on kprobes or?
It's at, yeah.
Oh, it's a feature of the function graph tracer. I don't think that's supported, but it should be, if you file a bug, I think it shouldn't be too difficult to do that.
Okay, thank you.
Can I run Perfetto in any embedded system? Because in the beginning you mentioned this is from Android, but like it is already working in an embedded system.
Yes. So if you you can build from source on most machines, like at least x86 and ARM is supported, and there are also release binaries that you can run. The Android is branded, but you can.
Second question: is there a Yocto recipe for Perfetto?
Is there a separate CPU?
No, a recipe, Yocto recipe. Like to build, it is already integrated in Yocto or not?
Okay, thank you. I didn't get the question.
And last question, can I capture the log and then open it in another machine? Like?
Yes, you can. It's the traces are completely self-contained and versioned, so it should be always openable any version of the UI. You might see slightly different information across UI versions, but it always works any.
Okay, thanks.
So I can answer or address the kernel shark topic because I've been using kernel shark and trace command for years for power management debugging, and I recently discovered Perfetto, which is one of the reasons I asked Zim to come and speak to us. So it's a selfish talk, but I can say for comparing kernel shark to Perfetto, one of the things kernel shark obviously doesn't have is the whole SQL side. So an example would be power management issues. If I want to debug a single suspend resume problem, kernel shark, I've been doing that for years. But if I want to do 1,000 of them and then start looking at averages and things that are happening only once in a while, then you get the power of the SQL side of things becomes really interesting. So it really, when you get huge traces or long-lived things or repeated events, you really want to add some query stuff. This is where it really shines.
Yeah, just to add a point about huge traces as well. So there is some browser limit on the size of traces you can open, and we do hit this limit at Google, like I think 1 gigabyte at some point. I think maybe it's 4 gigabytes now. But if you run into that limit, you can run Perfetto as a, like after you capture the trace, you can run it as a server effectively, and run and launch the UI. The UI will discover the port, and you basically, the UI is not, you don't open the trace in the UI, but the UI is speaking to the local instance of Perfetto, and at that point, your limit is your machine memory limit.
Got another online question for you. How does it compare to LTTNG, I'm not sure if I'm pronouncing it right, in terms of overhead, typically when trying to trigger on real-time events?
I have not used LTTNG either. Yeah, so.
Okay, thank you very much. It was a great talk.